Okay. So we got sequences here, and we can model them here with toothpicks. So we've got 3 toothpicks, and then 5 toothpicks, and then 7 toothpicks, and I can say, oh, I'm adding 2 every time, so this is 9 and 11. And this is what's called an arithmetic series because I'm adding each time. And there's what's called a recursive rule, which is describing how did I get the next one based on the previous one. And this is kind of intuitive. So in words, this would be like, well, I added 2 to previous term. Each one of these things in the series or sequence is called a term. And then for recursive, you always got to say where you started because you're always adding the previous. You got to start somewhere. So you say the first term is 3 in this case. And there's a rule over here. The rule over here for there's kind of a template here for arithmetic. There's an example, but basically it's the previous term plus what's called a common difference, or the amount that I'm adding every time. So in a formula would be, well, my first term is 3, and then my nth term, or like my 10th term, requires me to go get the previous term. So if that was the 10th, this would be the 9th, and then I'm just going to add 3 each time. So that's the recursive formula, is I get the next term by going and find the previous term and adding 3. And that fn minus 1, you're not really calculating anything there. This is just kind of means the previous term. If we created a table out of this, the one thing that's a little unusual, it doesn't really say is x 0 or 1 here. For sequences, we always say that, hey, we're going to start with 1, 2, 3, 4, 5. So the first one, if you want to think about this as an x and a y, my first x is always 1 and my first y is always the first term. So in a table here, it'd be 1, 3, 2, 5, 3, 7. And from that, we can do what's called an explicit, which is kind of what you're probably normally used to. Normally, we say, like, this is y equals something. And some of you can probably just look at this and say, well, oh, I'm going by 2's, so that's y equals 2x. But if I plug in 1 there, I need to add another 1 to get 3. And then 2 times 2 is 4, plus 1 is 5. That works, but it's like, well, what if I didn't see that, or I don't know how to do that? There's a formula for this, too. And the basic formula is f of n equals n minus 1 times d, which is that common difference, plus my first term. So if I plug that in, this one would be n minus 1 times 3, 2, because I'm going by 2, plus 3. And then if I actually distribute it, I can make it look like that, because 2n is there. That'll be a minus 2 plus 3. And then if I change that to an x, I have 2x, and the minus 2 and the 3 makes that. So that's exactly what we were expecting. So there's the formula for explicit, whereas this is the model for recursive, and that 3 that I plugged in is just, oops, that's actually incorrect. That should be a plus 2 again. Plus 2, common difference. Okay, multiplying each time is geometric, and I've got 4 triangles and 16 triangles, and if I count them all up, 64, and the next one would be 256 and 1024. So in this one, I am multiplying by 4. So in recursive, it's just like, well, what did I do to the previous term to get the next? And in this case, I multiplied the previous by 4, and then my first term is 4, and I had some students who were a little confused there. In this case, both my multiplier and my first term are the same. That's a coincidence. That doesn't always happen. But once again, and so in our formula, first term is 4, and then the formula for this is just last term times what the multiplier is. Okay. Down here, if I was going to fill in the table, 1, 2, 3, 4, 16, and 64. This one right here, the formula is f of n equals whatever your rate is, or your multiplier, so that's that 4, to the n minus 1, and I'll explain that in a minute, and then times your first term. So in this case, and that's my first term there, so in this case it would be 4 to the n minus 1 times 4. And what this n minus 1 does is if I plug in 1, 1 minus 1 is 0, 4 to the 0 is 1, so this is just, for the very first term, this becomes a 1 or kind of goes away, and that's why we always get the first term there, 4. And if we plug in a 2, 2 minus 1 is 1, 4 times 4 gives me 16. If I plug in a 3, it's 4 squared times 4. And so that's why that's normally n minus 1 if we create it ourselves. You can get formulas that don't have n minus 1 in them, but if you're using a table to create it, that's how you do it. So if I've got a list, I can look at it and see, well, is it arithmetic or geometric? And if I'm not sure, the way I can check is, well, if I subtract, this is why the thing you're adding is actually called a common difference. So I say, oh, that minus that is 3, that minus that is 3, that minus that is 3. That's definitely arithmetic. So that's arithmetic sequence. My common difference is 3. And then if I'm writing a I'm just going to do the explicit equation. The explicit equation here is f of n equals n minus 1 times 3 plus my first term. This right here, I'm adding 6. Oh, then I'm not adding 6. So this is definitely not arithmetic. It's probably geometric, but to find the common ratio, the r, if I do 18 divided by 6, that gives me 3. If I do 54 divided by 18, that gives me 3. And also 162 divided by 54. Okay, I'm always multiplying by 3. So my ratio, or my rate, is 3. And so my formula is f of n equals 3 to the n minus 1, and then times 6. And then I can always double check myself. If I plug in 1, I should get 6. If I plug in 2, I should get 18. If I plug in 3, I should get 54. This one we're not going to use as much. This one is actually really important. In fact, we've been doing things like this in class already, where we had a base number and then something raised to a power. And where that becomes really important is if I want to add up a bunch of things, especially like typically we've seen, like, I've got something invested in a bank, it's raised to a power, and I want to know, like, what's my total amount that I'm getting over a certain amount of time. And so what comes in there is, how do I add up a bunch of things in a sequence? So this worksheet here, which I'm not going to go through completely, says, oh, 2, 6, 18, 54, 162. If we add up the first 5, it's 242. We went through a bunch of calculations to figure out, oh, there's kind of a generic formula here. If I take the first term, multiply it times 1 minus the rate to the 5th, if I'm getting the first 5 terms, and divide it by 1 minus r, that should give me the first 5 terms. We actually plugged the numbers into that formula, starting with 2 as my first term. Our multiplier in this sequence was 3. We plugged everything in, and we got the same number that we got when we added up manually. So in fact, this will work for anything. So the general formula is the first term times the quantity 1 minus the rate raised to the nth power, where n is how many terms am I adding up, first 10, first 20, first 100, and then we divide that thing by 1 minus r. And so what that looks like practically in this problem down here, I'm like, okay, I need the first term, so f1 is 6 times 0.8 to the first. I had a lot of students who looked at this and thought the first term was 6 because the format was a little different here, but if I plug in the 1, it tells me what the first term is. So my first term is actually 4.8. And then if I want to add up the first, it's asking for the first 10 terms there, rather than add up all those little terms together, which would be kind of a pain, I can plug it in this formula and hopefully get something that's correct. And so 1 minus my rate here is 0.8. The thing I'm raising to the power is going to be my rate, or my common ratio, 0.8 to the 10th. And then I divide that by 1 minus 0.8. And the real trick here is when you put this in your calculator, you got to do this first. I see some students who do 0.2 to the 10th, and you can't do that. You got to do 0.8 to the 10th, which is a really small number. It's about 0.1 something. And then when I put all this in, if I do it correctly, I get 21.42. So you might want to try that and make sure you can get it plugged in your calculator correctly and get that answer. All right, I think that's good. Thanks.